look at our first set of reactions. And this type of reaction is called a free radical halogenation. In free radical reactions, we form a free radical as the intermediate. So if you look down here, A has a single electron, unpaired electron, and so it is called a free radical. Now, there may be non-bonding pairs on these atoms, or there may be bonds. We're not really concerned with that. What we are concerned with is that there is an unpaired electron. Any atom that has an unpaired electron is called a free radical. For this to occur, what has to happen is a bond must break, and when the bond breaks, we say that it undergoes homolytic cleavage. Homolytic cleavage means it breaks the same on either side. So this electron goes onto one atom, and the other electron goes onto this atom. We use a full arrow to show the movement of a pair of electrons. So when we're showing a bond breaking homolytically and then one electron moving somewhere, we use that half an arrow to represent only one electron. And so then this is the other electron. And so you see they're half arrows. So what are these half arrows showing? One goes here, one goes there. Now, when we go to form a bond, remember a bond is two electrons. So one from each atom has to join together with the other atom to form a bond. And so again, we show a half arrow and a half arrow, and we're showing that it's going between, so they're forming a bond. Okay, now you see how we write the mechanisms for these. Let's go through how a free radical reaction occurs. In free radical reactions, we see, of course, conservation of electrons. Now, we're starting with the least common of reactions, free radical reactions. Later on, we're going to be using the polar reaction and the full arrow, but both types of reactions, what we see are electrons are conserved. Notice what's happening here. We have an electron from a free radical. When we run a free radical reaction, what we do is we either put in something that has a weak bond that can be broken by light easily. For instance, halogens like bromine and chlorine, both you can just put them out in light and their bonds start coming apart. Homolytic cleavage to make two free radicals. And so that can be used. Or we can put something else in there that will come apart with just a little bit of the heat that is present at room temperature. For instance, peroxides. If you put a peroxide into a reaction container, the peroxide is constantly, the bond is opening up into two free radicals. It goes back together again unless it bumps into a molecule that it reacts with. So this free radical can come from a lot of different sources, either a free radical generator or from light breaking a bond. When this bumps into this molecule, what happens is this one electron basically reaches out and grabs one of the atoms. When that happens, one of the electrons that are in the bond that's holding that atom to the molecule jumps out and joins up with this electron over here to make a bond between the two of them. And so what you end up is a free radical bound to one atom. And then notice what is left over. This electron has to go somewhere, so it jumps onto B as a non-bonding free electron or a free radical. So see the conservation of electrons? Free radical, bond, bond, free radical. And in all of our reactions, you're going to see electrons are conserved. So it's either charge or unpaired electrons, whatever. Look for them to be the same. Here is the steps in a free radical reaction that we might have with chlorine and methane. There are 3 steps. There are 2 shown on this page. And so 3 types or steps that we see. Right here is chlorine. You irradiate it with a little bit of light. Ultraviolet light provides the best breaking of bonds, the right amount of energy. And what do you see is this bond in here separates. One electron jumps onto a chlorine, One electron jumps onto the other chlorine, and you end up with two free radical chlorines. One of these comes along and it's going to be careening around at high speeds, bumping into molecules. So here, this free radical comes along and bumps into a methane. Now, this is normally written as CH4, but we're spreading it out like this so you can see the bond between the hydrogen and carbon and methane. What happens here? The free radical grabs the hydrogen and wants to form a bond between the hydrogen and chlorine. That free radical, the one of the electrons in this hydrogen carbon bond jumps out and grabs that paired other electron to pair up and make a bond in here. The electron that's left over jumps onto the carbon. And this is what you see then, is you have hydrogen chloride and then a methane free radical. That methane free radical can bump into another chlorine, it can bump into another methane, it could bump into this molecule here, hydrogen chloride, anything that's in the container. There's basically madness ongoing because you have so many different types of reactions. Now what do? Is we focus on the ones that give us the things that we're interested in and the ones that produce products that we isolate. So we're going to keep it simple here and not look at all the possibilities. Here is one possibility that's very important to us, is this methane free radical has the electron reach out to this chlorine here. One of the electrons in that bond comes over here and joins up with this electron to form a bond between these two, and then the leftover electron in that bond jumps onto the chlorine. What's the product of that? A chlorine bound to a methane, we call this chloromethane, and then a chlorine free radical. Now, if we go back up here to this reaction, we can see what was the net result of this reaction. A molecule that has no free radicals becomes two free radicals. We call this type of reaction because it starts a free radical process. We call it initiation. So anytime you have a plain molecule break apart and make two free radicals, you have now had initiation. What happens down here in these two? Well, if you look, we have a free radical bumps into a non-free radical molecule, and it makes a non-free radical molecule and a free radical. So the net result is one free radical beforehand, one free radical afterwards. One plain molecule beforehand, one plain molecule afterwards. There's no difference in level of free radicals and bonds. So we call this propagation because you just generate another free radical and then it's free to go on in another reaction. So that's propagation. Then there is something we call termination. In termination, two free radicals bump together and basically terminate a free radical reaction because you take two free radicals and make a neutral plain molecule. So let's look at this example. We've got a free radical here and a free radical here. The free electron reaches out to this chlorine, this free electron reaches out to the other chlorine, and they form a bond between these two atoms. And there it is. What's the net overall reaction? Two free radicals become a neutral molecule, a non-free radical molecule. Here we go again. Free radical joins with free radical. Notice the two half arrows joining together to make a bond. And what do we get? A molecule with no free radicals. Two free radicals join together to make another molecule. So these are all termination reactions. The products that can result can be either a single product or they can be varied. It depends on what molecule you're starting with. If I look at ethane or methane right here, you can see there's only one type of hydrogen there, or one type of carbon, whichever you want to look at. You see there's a hydrogen attached to a carbon at the end of the chain. Hydrogens attached to carbon at the end of the chain. These are both primary hydrogens. Okay, they're the same. They're identical to each other. There's symmetry in this molecule. In methane, there's only one type of hydrogen. They're all identical to each other. So when these molecules, either this one or this one, react with either chlorine or bromine, there's only one type of product that's going to form. With ethane, it would be either a chlorine or a bromine on one of the end carbons. And with methane, what you would have form is either bromomethane or chloromethane. One product will form under a certain reaction condition. With many other molecules, what happens is there's more than one type of hydrogen, more than one type of carbon, same thing. And so what can result is more than one product. Here's an example. Propane has two different carbons. There's a primary carbon and a secondary carbon. Notice there are two different hydrogens also. Primary hydrogens, secondary hydrogens. As a result, we get two different products. If I look at this, you can see right here I have that same molecule written, propane and chlorine. I'm going to irradiate it with light, and what do I get? I can get substitution on a primary carbon, or I can get substitution on a secondary carbon. We call this molecule 1-chloropropane, and this molecule we call 2-chloropropane. Two different products form. Now, what affects the outcome? The first thing that affects the outcome is the stability of the intermediate. In the free radical mechanism, you form a free radical intermediate. So when this molecule reacts, it can form a free radical either where there's a free radical right here or there's a free radical here. If the free radical forms here, it's going to give this product. If the free radical forms here, it will give this product. Here, this is a secondary free radical, and it gives a secondary chloropropane. This is a primary carbon, so this would give a primary chloropropane. Two different products form, and the intermediates, free radical here or free radical here, have different stabilities. When the free radical is on a secondary carbon, it's more stable than when it's on a primary carbon. And we'll talk about later where the stability comes from. But basically, what do we see? The more carbons that are on a carbon, the greater the stability of the free radical. So tertiary free radicals are more stable than secondary free radicals, which are more stable than primary free radicals. So the intermediate with the free radical here on the second carbon, the secondary free radical, is more stable. And so this chlorine substituted here comes from an intermediate that hangs around a little bit longer and is easier to form than the primary free radical. But the numbers of hydrogens also affect the probability of a reaction occurring. If I look at propane, I see there are 6 primary hydrogens and only 2 secondary hydrogens. Because there are 6 primary hydrogens versus 2, there's more chance for a free radical to form from a primary hydrogen based on collisions. So a primary hydrogen is 3 times more likely to react. But the secondary radical is more stable. So it's more likely to form based on stability. What we find happens is both the secondary and the primary free radical form. And after we do research and we look at the outcome of reactions, what we actually find is both form, but the secondary substitution is slightly more likely to occur. And the greater the stability of the free radical, the more likely that compound is going to be to form. Okay, here's a problem for you to try. Draw out the structure of 2-methylbutane and determine how many different monobromination products. You can have more than one bromine be substituted on a compound, which kind of makes the reaction messy. But let's assume only monobromination occurs. How many monobromination products can you expect to have happen? In order to figure this out, you have to look at the different types of carbons and see how many different types of carbons you have to figure out how many different bromination products you can have. Figure this out and then restart the lecture to get the answer. Okay, the reaction that would occur here is written here. Here is 2-methylbutane, and we're going to brominate. So we use light and bromine. What can happen? Well, if I look at this carbon and this carbon, those two carbons are the same. So substitution here and substitution here give the same product. So it's only one product written for that. Okay? Where else can we look? Right here, that's a tertiary carbon. It's different from these two and different from these two. So we can have a bromine substituted there. Remember, never try to substitute a bromine or a chlorine onto a quaternary carbon, because it has 4 bonds already. You can't put a halogen on it. All right, well, let's go on. This carbon is different from the others. It's a secondary carbon and not the same as these three. So if substitution occurred there, I'd get a bromine here. And then this is a primary carbon. Now these are primary carbons, but this one's different. Why is it different? Because this methyl is attached to a methylene, CH2, here. This methyl and this methyl are attached to a CH, a methine carbon right here. So they're very different from each other. And you can see this is branched into a T. This one is just like an elbow. So visually they're different. And so what do we see? There are 4 products that result from monobromination. Okay, what type of step is this in the free radical chlorination of chloromethane? Look at it and then restart the lecture after you've determined your answer. Well, if I look at this reaction, you can see there is a free radical beforehand and a free radical afterwards. A plain molecule and a plain molecule. Free radical before, free radical afterwards. We call this propagation. What is the major product of the free radical bromination of T-butyl cyclopentane? Go ahead and determine what would be the outcome of this reaction for the major product. Hint, hint, think about stability. Okay, the major product would be this one. Why? Well, if I look, I've got primary, 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 quaternary, so bromination cannot occur there. Secondary, 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 and tertiary. Tertiary is most stable, so the most likely product is going to be from the most stable intermediate. So where is bromination going to occur? Right here on a tertiary carbon. If there was no tertiary carbon, then you would pick a secondary carbon. If there's no secondary carbon, then you would pick a primary carbon, of course, and the primary carbon with the most numbers of hydrogen.